Ladies and gentlemen, I'd like to welcome you to our BASF Ultramid Expand webinar, Expand Your Ideas. This is a novel polyamide-based particle foam for structural applications and more. And in the next 30 minutes, we would like to expand your ideas. First of all, I want to give you a brief overview about the outline of today's webinar. We start with a small introduction, then we will take over to a general overview about the particle foam itself, and afterwards a deep dive session about the technologies around the Ultramid Expand and how you can expand your ideas. Finally, we close the webinar with the Q&A session. You can ask the questions in the chat anonymously, and afterwards we will provide the answers to you. First of all, I want to introduce our speakers of today's webinar. Next to me is standing Patrick Spies. He is a specialist for product development engineering plastics. And this here is Andreas Wüst, our CAA simulation expert, and also for part design and customer relations. Myself, I'm René Holschow. I'm the respective segment manager for transportation. Let me give you a brief overview about the history of polymer foams at BASF. It started all roughly in 1949 with the well-known styropor. The next development was Styrodur in 1964. And if you go along on the timeline here, you can see well-known names like Basotect and Neopor. And in 2013, there was a new material available on the market. It's called Infinergy, a ETPU-based material. And if we come to the near future, or today, in 2023, we launched our new Ultramid particle foam, Ultramid Expand. But that's not the end, expect more to come. And now I would like to hand over to my colleague Patrick Spies.
Yeah, hello from my side. So I want to give you a general overview about Ultramid Expand particle foam. And as we already mentioned, Ultramid Expand, it's a particle foam, and particle foam is a little bit special topic. So I like to start with a brief introduction about particle foams. So what are particle foams? Particle foams are molded parts from foam particles. And here on this slide you can see some of these foam particles. So we as BASF, we typically deliver foamed polymer particles to the customer. That is the case for Ultramid Expand. Or we deliver expandable particles, as it is the case for Styropor and Neopor. And these foam particles are then fused together, most often with hot steam, to shape molded parts. Particle foams are typically closed-celled foams with a cell diameter of 100 to 150 micrometer, and particle foams are thermoplastic materials. So Ultramid Expand, it's a relatively new, a relatively young product, and on this slide you can see our current product portfolio. So far we have developed 3 grades here. On the left side you see an uncolored, natural colored grade with a particle size of 2.5 millimeters and a bulk density of 290 grams per liter. From this material you can obtain shape molded parts with a part density of 340 grams per liter. In the middle you can see the same product in black color with an additional heat stabilizer. And then we have a special product which consists of small particles of 1 millimeter. And this material is very interesting if you want to produce big parts with thin areas. So on this slide you can see a demonstrator part which we produce from Ultramid Expand particle foam, and which you can also see in the background here. On this demonstrator part you can see what opportunities and possibilities you have with our new material. So especially in this part you see we have a relatively big parts, and there are holes in the parts and thin wall thicknesses which go down to 1 millimeter. Additionally, the material is laser markable. You can incorporate threaded inserts, and you can also realize cutouts. So this demonstrator we produced on our own mold, and we are also happy to send out this demonstrator to you if you want to get an impression about the material appearance. Let's talk a little bit about the properties of Ultramid Expand. So Ultramid Expand is a particle foam based on polyamide, and due to this fact we have a superior heat resistance. On this slide you can see a photo where we put an iron on top of the Ultramid Expand particle foam, and this demonstrates the high heat resistance which the material has. So in principle the material is in the short run stable to temperatures over 200 degrees Celsius. We have a high heat deflection temperature, and we have excellent mechanical properties even at temperatures above 120 degrees Celsius. Okay, to illustrate you the good mechanical properties at high temperature, I put an so-called DMTA measurement on this slide. So in this diagram you can in principle see the material stiffness on the y-axis and the temperature on the x-axis, and the blue curve belongs to our polyamide particle foam. What you can see in principle here is that the Ultramid Expand particle foam has a relatively high stiffness even at high temperatures above 100 degrees Celsius. At 220 degrees Celsius we reach a melting point, and then the material just melts. For comparison, I put a gray curve in this diagram, and this gray curve belongs to a polypropylene particle foam. Also, polypropylene particle foam has a high mechanical stiffness at room temperature, but if you come to elevated temperature, the material loses relatively fast its stiffness and melts in the range of 130 to 140 degrees Celsius. Not only the mechanical stiffness of Ultramid Expand at high temperature is remarkable, also the so-called heat aging performance of Ultramid Expand. Ultramid Expand consists of a special polyamide formulation which is stabilized against thermo-oxidative degradation. So in this diagram you can see a so-called heat aging experiment. We put the material for 2000 hours in an oven at 120 degrees Celsius, and after that we carried out a compression test. And what you basically see in this diagram is that the material hardly loses any compressive strength. So besides this, Ultramid Expand also offers even more benefits. So because Ultramid Expand is based on polyamide 6, it's stable against most automotive liquids like aliphatic chemicals, oil, greases, fuels and solvents. And I think one of the most remarkable aspects here is that the material is processable in the cathodic dip coating. So in principle you can produce a structural inset from Ultramid Expand, incorporate it in your body and white structure, and put it through the whole cathodic dip coating, including the afterburn oven. Ultramid Expand will not contaminate your dip coating baths, and it will also survive the afterburning oven. Ultramid Expand, it's also laser markable. So in principle you can also use a standard laser which you also use for the marking of compact plastics. And like any other polyamide, it's gluable and weldable. So here you can use standard adhesive which you would also use for polyamide. And regarding welding, you can use technologies like hot plate, hot gas, infrared and vibration welding. So let me just talk a little bit more about the properties of Ultramid Expand and what are the similarities besides known materials like EPP and the differences. So let's talk about the differences. If we compare our EPA with known EPP, polypropylene particle foam, we see that the density of our Ultramid Expand particle foam is significantly higher than the density for the commercial available EPP. So our particle foam has a density of 340 grams per liter, while for EPP the maximum density which is applicable is 200 grams per liter. Very important aspect is the maximum use temperature. So our particle foam can be used up to temperatures on the long run to 150 degrees Celsius, while for EPP here you would already reach the melting point. For Ultramid Expand we offer small bead sizes down to 1 millimeter, which is especially interesting if you want to produce parts with thin wall thicknesses. The material has a high compression stiffness, and what is even more important, a high compression stiffness at high temperatures. Let's talk a little bit about the similarities. One very important similarity is that you can use exact the same processing technology for Ultramid Expand than you would also use for EPP. So you can go on a standard steam chest molding machine which you use for EPP, even take the same aluminium mold and process Ultramid Expand on these machines. You can really realize big parts, which is typical for particle foams, with our Ultramid Expand, and due to the small particle size we can also realize challenging geometries. And a very important aspect is that you have quite low tooling costs here for large parts, since you can work on these cheap aluminium molds. Let's talk a little bit about the production process. So we at BASF, we will provide foamed polyamide particles, which you can see here on the slide. So basically Ultramid Expand is produced from a special polyamide mixture which come from our BASF Verbund, and these polymer particles, or these foamed polymer particles, have a bulk density of roughly 300 grams per liter. On the photo below you can see a microscope picture of such a foam bead. On this picture you can nicely see the closed cell foam structure of our product. These foam beads are then delivered to our customers, which then typically fuse the beads together with steam chest molding technology. Very important aspect again is that you can realize very big or even huge parts with this technology. You have low costs for the mold, and very important aspect, this is a real drop-in solution for existing processing technology. That means you basically also can work with the same steam pressures of roughly 4 bar, which you also use for the fusion of EPP. And on the picture on the right side, you can then see a cut through the foam beads. Here you can nicely see that the former single beads are fused together to a closed cell foam structure. So, and now I'd like to hand over to my colleague Andreas Wüst.
Thank you, Patrick. Now it's my turn to talk a little bit about technologies that we have developed around our PA foam. And yeah, we first take a look and try to define what are we talking about. If you look at the density of that material and you compare it to an injection molding grade, then we have about 25 to 30% of foam density. So the word foam does not really cover what you have. It's not a foam of a mattress in a bed. It's more like wood. And what we have heard from Patrick already is we have a temperature advantage, we withstand the cadaveric dip coating, and we can use a standard foaming process. The part that you have seen, Patrick has also mentioned it already, it has about a size of 250 times 250 millimeter. You see it's a battery cell holder demonstrator, and as Patrick already mentioned, you can order those parts if you like, if you want to see one. So the question now is, what can you do with our material? And you will see you can do a lot. First of all, you can use it as an insert in a metal structure. We can survive the KTL, we can put our material in what you see here, a kind of cross-section made of metal, of steel and aluminum. And it can be integrated so that the cadaphoretic dip coating liquid flows all around that. But for what is this material when it's in such a cross-section? It's quite clear. If you have a hollow cross-section which is only made of metal, then this cross-section will have a very pronounced buckling point. And with our foam that you put inside, we can shift this buckling point to a higher force, and we can also increase the stiffness a little bit. And you see that here on the red and on the green curve that we have an energy gain when we put our material inside such a metal cross-section. Another thing where we can also combine our material with other materials is we can use it as a core layer in a sandwich core. So the sandwich can either be two metal layers on top and bottom, but it can also be a plastic layer. So, and as I already said, we can shift the buckling point to much higher values and increase the forces. Another thing that you can do with our foam is you can overmold it. So let's have a closer look here. On the left side here you see an insert of injection molded tool. So this is the core side, and the polished area is normally made of metal. But what we have done in order to show and to prove that we can overmold it is we took away this metal part. This is the green area that is indicated here, and then we replace this metal part by foam inserts. So here on the left side you see the CAD model, on the right side you see the real milled parts. These are not foamed in place, but they are milled out of a plate. And also what you see is you have again also ribs into that foam insert, so they are a real extension of the cavity. And what is done here is, you see on the left side the open mold, you put the foamed core inside, and then we overmold it with a standard injection molding process. And we have tried several materials, for example a non-filled polyamide and also glass fiber filled polyamide, and the core withstands those pressures that arise during this filling process. The good thing, and you see that on the right side with that sketch here, internal connection, the foam core is not just something that is a core that builds some solid volume. It is an extension of the cavity. So by drilling holes in the core, you can really make new parts, a new class of injection molded parts, where you have inner connections that build a kind of internal skeleton in the injection molded part. To summarize, Ultramid Expand can be overmolded with polyamide, and we can then do extensions of the cavity. We can make parts where undercuts are possible, and we have a single material recyclability here. So it's basically polyamide on the inside and polyamide on the outside. If you use our material as a core, then of course it's not as stiff as metal cores are. So there is a danger if you have an asymmetric filling that the core is shifting, and you see that on the lower left. This is a simulation that we did, is a core shift simulation, where you see the core deforming and is touching the mold. The good thing is here, as you can see with that simulation, we can simulate it by using the pressure that we have analyzed during a filling injection molding simulation. And then we can use that pressure to load that on the core and see how much it deforms. And so the simulation can help to develop and evaluate countermeasures if the deformations would be too high. Simulation always means that you need to characterize the material. And here you see the tests that we have done. You see bending tests, tensile tests, compression tests, and we have derived the stress-strain curve, and we have also characterized that. And our Ultrasim model, Ultrasim material which we use for those
materials, also for injection molded materials. We also have the material models ready for the Ultramid Expand foam. If it comes to using the foam, you can use it as a crash insert. And this first slide shows Ultramid Expand as a single material part. So just put the part with its very high compression stiffness and higher temperatures, and then you crash it. And what you can see here is that we can really simulate also the limits of that material and can basically predict the force curve that you have over the displacement. But you can also use Ultramid Expand as a combination. So this here shows a combination with injection molding. On the left side you see an energy absorber. This is a patented structure which is basically serving energy and conserving energy and absorbing energy. And on the right side you see the same structure which is filled with our Ultramid Expand foam. And here you can combine injection molded and foamed polyamide by overmolding. You can also do overfoaming, and you can also do a post connection. And all that leads in the end to higher forces and higher energies that you can absorb with that structure. The foam, if you look at it from an engineering point of view, it acts a little bit like a hydrostatic fluid, so it distributes the pressure in all directions, and so we can achieve a constant load distribution internally in the part. Other things that we did here is a plate that we have simulated. You see on the left side without and on the right side with ribs. And by making a stone impact test with a 40-kilometer impact, you see that without the ribs, the stone punctures the wall and we have a very large failure. On the lower side, you see that we only have minor damage if we put ribs on. And here again, simulation can help to predict what's happening before you build such a part and such a tool. Other things, when it comes to using the foam in a 2D way, is we can fold the material. If you put some grooves in, which we also have simulated here, you see that in the middle, you can take the two-dimensional part and bend it up in a kind of 3D box shape. And if you put some polyamide glue inside those grooves, then you can also fix those 90-degree bending corner. This slide shows a completely different thing. Now it's all about simulation also, but we do not describe with the simulation how the foam material reacts when it's foamed. We here now simulate the foaming process and the filling process itself. This is a particle filling simulation with a discrete element method, and what you see here is the interaction of about 2 million parts on the computer. All have their own density, their mass, their velocity, and they can interact with each other. And we can now see and judge before we build the tool if we can fill the tool with the injector points that we have looked at. To summarize, our virtual description goes from filling simulation. You see that on the left side. We also do the packing simulation, where we see if those air traps can be overcome. And then what I already showed is we simulate the finished part made of the foam in a mechanical way. Of course, you have to fix those foam parts, and here we also have investigated how we can fix it. What you see on the screen here now is we looked for screws. So on the left row you see self-threading screws, on the other side you see metric screws. You can make metric screws with inserts that you put in after you have foamed the part, but you can also incorporate those inserts while foaming so that the part comes out of the foam mold and has already a metric thread inside. Other things you can do is you can weld it. Patrick already mentioned that. Hot plate or hot gas welding, infrared welding, or vibration welding is possible, and this is also a possibility to combine our PA foam with injection molded parts. This was what I wanted to show about the technologies around the foam. I'm very sure that you have ideas about that. Please contact us, and you can also later on in the Q&A section ask us questions, and we try to answer them as best as we can. Thanks.
Thank you, Andreas. Thank you, Patrick, for this very impressive overview about our Ultramid Expand. And with this, we hope that we could expand your ideas about applications, new applications. Contact us. And having said this, we open the Q&A session. Thank you.